visually seen the antennas, and basically it is basically as a rod or a wire. But the new generation have seen it in forms of the antenna which is inside the mobile, and antennas have touched since it is in everybody's pocket or hand. So it in some sense it has touched everybody's life, we can say. So I will also briefly explain how this antenna radiates. So in order to understand how radiation happens, because nothing is visible, we just have a mobile and something is going out of the this handset, and somewhere miles away it is being received. So how does this happen? So basically it is very basic thing that we have read in physics to all those people who are not working in the field of antennas. So I just want to tell, like, this is very preliminary things that we have learned in maybe in 12th standard and all. Basically the electric field and the magnetic field are the two main components. Basically time-varying electric field and magnetic field, not just electric field and magnetic field. It is the time-varying electric and magnetic field which is the main responsible for radiation that is happening outside of your mobile or any antenna. So basically this is two arms of a dipole. Dipole is basically a metallic thing. So this is at a negative potential and this is a positive potential. So we have learned in our basic physics that when there are two unlike charges, then there is an electric field that surrounds that potential. So there is an electric field which is there. So if there is a time-varying electric field, according to Faraday's law, there will be a magnetic field which will be encircling this electric field, perpendicular to it. So once, depending upon the wavelength, once there is a certain cycle happening, this electric field and magnetic just detaches from this dipole field, and once it is in the space, the electric field and magnetic, there is a recurrence happening. So that is how it is, the electric and magnetic fields are sustained in the space, and that is how the information or the energy is being transferred. So that is the basic of how radiation is happening, and this mechanism of radiation was explained by James Clerk Maxwell long before Hertz had demonstrated it experimentally. So this is a phenomena that we can say, like, it was analytically first described, then only experimentally it was proven by Hertz. So this is a horn antenna. So here also we can see the electric fields are traveling it as is in a transmission line. But as it touches this end, that there is a sudden discontinuity that is happening, the electric field just detaches away from this structure, and accompanying this will be a magnetic field, and this is how radiation is happening in the space. So I'll also discuss the types of antennas so that it will be more aware to people who are working or who are studying. So we have this wire antennas and basically dipole, monopole, which are made up of wires. So they are definitely called wire antennas, and this we have seen in our automobiles. The one working at VHF or UHF range that you have in your are basically wire antennas. And then there is something called aperture antennas also. This antenna, as we saw in the definition, it says like it's a metallic object that radiates or receives waves. So one peculiarity of this aperture antenna is that, like, if you have a metal, a hollow metal, basically we call it a waveguide, and if we cut a slot in it, there is a disturbance happening there, and then it starts radiating. So this comes into a type of aperture antenna, and the horn antenna is basically practically you can see in all the DTH antenna which is installed in most of our houses nowadays. So basically you will see a reflector, and there is one small feed in front of it, and that is called a horn antenna. And they have been one of the antennas which have been used in spacecrafts, like before other antennas, the printed antennas have come into picture, and they are able to handle very high power because of its structure. And the other thing that I was just talking when I was discussing about the horn antenna is a reflector antenna. And this is, I think everybody has seen nowadays because of the DTH. The DTH antenna basically works at Ku band frequency, and it is one of the antennas that has been extensively used in satellite tracking as well as in radars. And basically in communication also it is extensively used. And then the one antenna that has been in foray since 1970s and impacted most of the scenario of communication, radar, space is this microstrip antennas, more popularly called as printed antennas because of the structure. It is basically a metallic strip of copper, very thin, almost less than a micron, which is etched on a dielectric substrate. So it basically gives a very low profile and a compact antenna shape. So compact antenna. So basically this is the antenna that is generally used in the mobile phones that we all have. So since it is also called a printed antenna because it is basically manufactured using the photolithographic technique, which is generally used in the PCB manufacturing. So that is why it is called microstrip antennas, and we can see like these antennas have almost entered in all the fields of applications, such as it is used in aircraft, spacecraft, satellites, missiles, car, mobile phones, everywhere. So even though it's not visible in your mobile, that is the one which is inside your handset every time. So the other type of antenna is called array antennas. Basically, they are arrays. Basically, like array is a repetition of number of items. So here, what you do is you arrange the single element. For example, the patch element you can arrange in sort of a number of rows and some columns. And basically, it is used to increase the gain of the antenna. It is used to shape the beam, and similarly, the waveguide openings that I just explained, the aperture antennas, that can also be, a number of it can be aligned such that you can have a definite beam, definite side lobe levels, and all those things. The characteristics that will be I'll be talking about later. So, so how do we characterize? What are the different parameters that an antenna is associated with it? So there are different ways an engineer looks at as an antenna. For one particular engineer, he may be like, you can consider it as a circuit antenna. For example, if he's a MIC circuit, he may be more interested in knowing like what is the input impedance of an antenna so that he can match it. For a person who is in the receiver side, he may be interested in the antenna noise temperature. And then for an antenna engineer, the return loss, how much loss is there, how much the antenna is accepting the power that is going into it, and the impedance bandwidth. That is one of the important characteristics when we see antenna as a circuit. But this return loss and impedance bandwidth comes across as an electromagnetic parameter also, but it's like a amalgamation. So the electromagnetic parameters basically consist of the field pattern. Like once the electromagnetic energy is radiated in space, so it is we basically consider the radiation pattern, how it is spread across the space. So in that particular pattern, the beam width, the directivity, the gain, these parameters are very important. The radiated power, how efficient is your antenna. And the one important characteristics of the radiation is the polarization. Polarization is basically the orientation of electric field that is emanating from your antenna. So depending upon the polarization, whether it is a linear, circular, or elliptical, the various functionalities of the antennas also depends. So these are some of the electromagnetic parameters. And as an engineer as a whole, as an antenna designer engineer as a whole, sometimes this physical quantities restricts your design. For example, the given size in your size in a system. For example, suppose let us take an example of a mobile. So in the mobile, now we are seeing like the size of it has been reducing. So the availability space that is given to you. So that may be one of the important criteria for you to select a particular antenna. So these size, weight, profile, shape, and now I can also add cost. Like if you see, there are number of types of antenna and there are different types of antennas available. So what is the cost implication? That is also one important aspect of as a designer that has to be looked upon. So let us just dwell upon this radiation parameters as a radiation pattern. So as I told you, as soon as the electromagnetic energy is out in the space, so it is only the radiation pattern that is in the space. So basically, this radiation pattern is a 3D pattern, 3D in nature. Generally, we only see a pattern like this. If you ask any of the working people over there, we only visualize a radiation pattern in these two planes. As a main beam is there, and then there are these lobes. This basically are called side lobes. And the one which is on back of the antenna, you can imagine the antenna placed in this XY plane, and then the radiation is happening perpendicular to it. So, but there are antennas which can along it can radiate. This is basically called a broadside antenna. The one which radiates along it is called an end-fire antenna. So basically, it's a 3D pattern which is there in the space, and then this radiation pattern is a graphical representation of what, and it will tell you what are the different features of the radiation pattern. So, and this is basically formed in space depending upon how you excite your antenna. So when we cut this into two principal planes along the E plane, or in the plane containing the E vector, electric vector, we call it that E plane. And then when we cut along the H plane and also at the direction of maximum radiation, we call it the H plane pattern. So depending upon the radiation pattern, basically antennas, we can classify it as an isotropic, directional and omnidirectional antenna. Isotropic is basically a hypothetical antenna, but it serves as antenna which can be like certain terms in antenna like directivity and all are all considered with respect to isotropic antenna. So it is a hypothetical antenna which is having equal radiation in all directions. So in a 3D, you can imagine it to be as a sphere. And then directional antennas are antennas which is having a property of having some directions. For example, this antenna is a directional antenna. What it has done is basically, this is an isotropic antenna. So what the antenna has done is it is focusing its energy at particular direction. So that at a particular direction, you can consider this line as an radiation by an isotropic antenna. But by focusing all these energies, all the extra energies which are going in compared to the isotropic antennas, in a particular direction, we are having that focused beam. So this is a directional antenna. And then we have also called a omnidirectional antennas or omnidirectional pattern, where it is having direction in one particular beam. For example, this is a typical 3D pattern of a dipole antenna. So basically, in this plane, it is having omnidirectional. It is circular in nature, but in this plane, it is having a figure of 8. So this is basically called a donut pattern. So a donut pattern is an example of a donut is an example of a, you can correlate it with an example of an omnidirectional antenna. So I will just briefly explain some of the radiation parameters that I will be explaining during the case study that I will be presenting later. So I'll not be telling all the antenna parameters, but as IEEE has given definition for antennas, so and the IEEE has also defined in its one of its chapters all the definitions of antennas. So anybody interested in knowing more, or because if you go to different books, you will have different parameter definition. So I would, if interested people can go to IEEE and then get the definition, like what basically it describes all the radiation parameters of an antenna. So gain, as I told you, as I was mentioning, how this is a pattern of an isotropic radiator, but when you focus it into a particular direction, that amount that you get from that antenna is basically a gain. Basically, it will tell you the gain of that particular antenna. So for an isotropic radiator, we consider it as a 0 dB. So gain is in consideration with that parameter. So the other is the beam width. Beam width is basically the angular separation between these two identical points opposite of the maximum beam pattern. So, and if it is taken in a half point of this thing, then it is called a half power beam width or 3 dB beam width of the radiation pattern. So directivity is also basically the radiation intensity in a given direction from the antenna to the average radiation intensity. And directivity and gain have a slight correlation between them. Only thing is directivity, when we consider, it is basically only considering the radiation pattern only. But when we consider gain, then we take into consideration the antenna efficiency. Basically, all the losses, the gain will take into consideration all the losses that are present. So basically, the efficiency in an antenna is basically dependent upon the reflections become a mismatch between the transmission line and the antenna, as well as because the antenna is made up of conductor, so you have having conduction losses and also dielectric losses if it is a microstrip based antenna. So these two parameters will basically bring down the efficiency of the antenna, and when we consider that in terms of directivity, we will finally arrive at the gain parameter of the antenna. And as I was telling, polarization of the electromagnetic wave is very important, and for the antenna also it's very important, because when the interaction of the electromagnetic waves with the surfaces, for example, I will tell in terms of a radar. So, for example, if your antenna is transmitting, or your system is transmitting a vertically polarized wave, so this interaction between the electromagnetic fields and the vertical targets may be more. Vertical targets will be more, so you'll get more returns from it. So there you will prefer vertical polarization. And in the horizontal polarization, for example, if ships are there, so the cross section of the ships, as you see, are horizontal. So there you prefer horizontal polarization. But I would like to tell, like, there is still very vast ambiguity on what polarization choose for radars. But this explanation slightly brings out like why polarization is important. For example, when in case of some meteorological application, weather radars and all, they use circular polarization, where the electrical field vector is moving in a circular fashion in space. So that is basically to remove the clutter due to rain and all. So that is how a particular polarization is chosen, and polarization plays a very important role in antennas. So now we will go to the topic of the session today. So first I will just try to briefly explain this radar. So radar is basically an acronym for radio detection and ranging, and is one of the EM electromagnetic sensor that is used in our military operations and all. So radar basically we have the main antenna role is to transmit the electromagnetic energy given by the transmitter. So I hope like whoever have attended last year's lecture of Sushma, so she also have given a broad overview of this radar. So the transmitter basically gives the antenna power to the radar. So the power to the antenna, electromagnetic energy to the antenna, and then the antenna radiates. The radiated energy is intercepted by the target or any object, and then on reception on hitting up the electromagnetic by the target, the part of it gets reflected, and again it is received by the antenna, and then it is sent to the receiver and processed, and to the processor it is detected the presence, and then the further thing like tracking and all are being done in a radar. So if we come to the applications of radar, there are a number of applications. I have mainly brought out some 5 applications. So military applications basically for our air defense, for target detection, recognition, and it also helps in guiding the weapon to engage to the target and destroy it. So that is how this weapon control comes for the radars also. In missile systems, it is used to guide the weapon, and in general, it is used to identify enemy locations. And one more application of radar is in imaging application. So by using electromagnetic waves, we can image a particular area. So in that case also, it will help in identifying enemy locations in map. The other commercial application of it is in air traffic control. Most of our air traffic control applications, they use radars only to control air traffic near airports, to guide the aircraft to land in bad weather, for ground and aircraft vehicle positions, movement and all. So in air traffic control, radars are heavily used. And in remote sensing, to observe the weather, planetary positions, and monitor sea ice to ensure smooth route for ships and all. Remote sensing, it is widely used. And in ground traffic control, to determine speed of the vehicle. And right now, there is a lot of research and development going in autonomous vehicle, and and radars, the compact radars at very high frequencies are one of the research areas over there. So the size of antennas and all will be very less at that time. So a lot of R&D in the radars for autonomous vehicles is going on. So and the other is in space. Space also radars are used for safe landing of the space vehicle to observe the planetary system and track and detect satellites, and also to monitor the meteors. Hello? Hello?
Hello?
Hello? I am not
Yeah,
listening. Hello?
Yes, ma'am. Yeah. Yes, ma'am.
Okay, my video stopped actually, madam. I will continue.
Maybe that will be because of the bandwidth issue.
Okay. I can continue, madam?
Yeah, you can continue. Yeah, you're audible and your slides are also seen.
Okay, fine, madam. So if you see the radar scenarios now, so it is having many functions as of now. So it can be it is basically a multifunction in the sense like a radar in an aircraft has to have a air to sea mode, sea to sea mode. So air to sea, not sorry, sea to sea. It is air to ground mode. So radar has to have a multifunction capability, as well as it should have multi-mode and multi-band depending upon the scenario in the in a wartime or so. So it should be equipped with multi-band features, as well as it should have multi-mode operation capability. And now most of our radars are spread across the length and breadth of the country. So all the radars have to work in unison, and that's why network-centric operations of all the radars are very, it's a requirement of that. So if you see, as the technology advances are there, equally there is an enormous requirement for radar hardware, electronics, as well as software. And antenna is one area where there is a lot of research going on, how to make a compact antenna, how to efficiently make an antenna, especially for arrays as well as large arrays. Antennas in the some more than 10 kilometers, not more than 10 kilometers, more than 10 meters, how to make large arrays. So antennas for those big size and antenna arrays are also on there's a lot of research going in this area. So like in communication, we are having the basic Friis transmission equation. Basically, that governs the communication link performance. We have in radar the radar range equation. Basically, it is an equation which considers the range parameter. That is one of the crucial parameters for a radar, because radar means it is used for ranging, so distance. So this range, basically the distance, is one of the important parameters of the radar, and this radar range equation gives the dependency of all the system parameters which is governing this range. So once the range is fixed by the system for that particular radar system, so now all the parameters like the transmitted power, that's what Sushma was talking about in last week, the transmitted power. So now let us see on the antenna side what are the things that is most prominent here. So we see here gain of the antenna, lambda, that is wavelength. So it is directly related to the frequency of operation of the system. So gain and the wavelength are directly over here, which is one of the very critical parameters which is governed by the antenna. So the antenna system performance highly influences the radar performance. So as well as the efficiency can be improved by the beam formation, and this is basically done by the antenna. For example, if you want to cover a large area, you can have shaped beam. You can have size of levels that you can control in your antenna. So that flexibility the antenna gives in case of a radar. So I would also like to share what are the different types of antennas that are basically used in radars. So initially when radars came into picture, basically radars were more, a lot of R&D was in radar as a system whole from the World War II. So from the World War II, you can see there's a lot of developments that have come in the area of radars. So basically, those radars were mechanically scanning radars. Basically, why we want to have a mechanical scanning is, as I told you, in order to properly detect the target in a particular location, you want the beam to be a narrow beam, not like an isotropic radiator or an omnidirectional light antenna. So you want the antenna to have a high gain or a focused beam. So that is why this parabolic reflectors, they give a focused beam. And here also you can shape the pattern, shape the radiation pattern. But earlier, mostly it is focused beam only. So, and since it is a focused beam, so you will be able to only cover a small area. So, so in order to scan a volume of the, in order to see all the volume that is there in the space, what you have to do is you have to scan it. So that scanning is basically done either through this motor drive. So it is mechanically scanning antenna. So you have an antenna and there is a drive, and this is by MIT, and this is our radar developed by LRDE, and this is a parabolic reflector fed by, this is a horn antenna. So this is an antenna which is mechanically rotated to scan the full volume. Then the other type of radar is a hybrid mechanical and frequency scanning antenna. Here it's a combination of mechanical as well as electronically scanning. In the sense, for example, this is an antenna termed as Ashlesha, where in the azimuth direction, in the azimuth direction, what you do is you have a you mechanically scan it in the azimuth direction, while in the elevation direction, in one plane you are mechanically scanning, in the other plane the amplitude and the phase of the radiating elements are controlled that you can scan it. There is a electronically you can scan the beam without moving the antenna. So this is a hybrid mechanical and frequency scanning antenna. And another is the electronically scanning antenna, where the antenna elements in the antenna array are being, the amplitude and the phase that is going into the antenna is being controlled so that you can electronically scan it. So here the speed which the beam switching that you can achieve in this electronically scanning is in milliseconds as compared to the in some seconds, because due to the inertia of the mechanical drive and all. So here that is the major advantage of electronically scanning radars. So these are the three types of radars that is available. So for an antenna design, let me share the challenges and opportunities that are there. So there are enormous challenges for an antenna designer, as I told you, like basically the functional parameters. Initially, when I had joined LRDE, at that time, the functional parameters were there, and we had to certain define it. But over the years, as I experienced thing and all, so at that time I found like the size, weight, and all are now becoming the challenges. So as I was telling, like they have some restriction on the size and the weight, because now we are also transforming from a ground-based system to airborne system. We are also working in airborne radars and all. So there, the size, weight, and power are more of a constraint there. So that sometimes dictates our design. So that represents a challenge for an antenna designer now to come up with new techniques of feeding it, come up with new architecture for the antenna. So these are the challenges that we face in the radar scenario. And equally, it will be there in other communication and all also, because now as we are moving towards 5G and all, their wideband requirements, compact antenna sizes, and bandwidth, very precise bandwidth, because now we don't want to flood. Now bandwidth is very important parameter for any antenna design. So those parameters dictate the type of antennas that we choose, and then the design that we come up to meet the requirements. So there is a lot of challenges as well as opportunities in the design of the antenna. And then the other thing is now, as an opportunity is things I can tell, like there's a lot of advancement in the computational capability of the machines that we are using. And there are a lot of software, electromagnetic software, so which solves the Maxwell's equations and then gives us accurate results. For example, when I started my journey as an engineer, so I think I had to do some 3-4 iterations to finally fine-tune my antennas. But now that design cycle has reduced thanks to the computational power, because computational power of the PCs, as well the advancement that has come in the software, that now we generally earlier used to see like there is a frequency, generally there used to be a frequency shift. So when we are designing that antenna, we used to keep in mind, okay, after fabrication, I will have some 30 or 40 mega shift in my return loss. Or parameter that depends. So we used to design accordingly. But now we are seeing like since the software is also improved and all, so the design development cycle has reduced. So, but one caution to all the students, especially because they may be thinking like, okay, software is there, software will do it, and nothing to worry about it. But I just want to highlight this quote by founder of Sonic EM software. He told like, he had mentioned that no single EM tool can solve all problems. An informed designer must select the appropriate tool for the appropriate problem. So you need to have a background of electromagnetic theory, because all these softwares will work on different techniques. Some will work in FEM, FTDT, PO. So you have to appropriately choose depending upon your requirement as well as the complexity of your problem. So this is a word of caution to all the students over there who will think like, okay, the system will do it and we will get result. But a lot of basics is required to understand this. So I'll just briefly give some glimpses of the antennas that are basically used in some of our radars. Indra, that is Indra Doppler radar, is one of the premier and pioneer radars of our LRDE, and it basically consists of a parabolic reflector fed by a horn. And this is a doubly curved reflector antenna for a project for a mountainous region. And one more thing I wanted to tell to the audience over here is the antenna design is a combination of electromagnetic professional as well as a mechanical as well as a fabrication if it is a microstrip based antenna. For example, this antenna, if you see here, has to be packed in a rope. It should be able to be carried by a human being in a mountainous region, or it should be transportable by some animals like mules or donkeys in some mountainous region. So the construction of this antenna, since this was at an L band, it had to be mechanically thought of how the weight can be optimized, as well as how it can be made fittable, and then it had to be quickly deployed. So those constraints are there from the mechanical side. And then after doing that, our electromagnetic performance should also not affect. So that is one of the challenges when we are designing an antenna. So over here, you can see like unlike the dish antenna that you are seeing in your home for your DTH, which is a flat and a solid reflector, you are having ribs. This antenna made up of ribs. So basically, this is done to withstand the wind loads at such high mountains, basically more than 70 or 80 kilometers per hour wind loads. So this is one. So during the development of the antennas, it is not only like the parameters that we are working on it, but as an end product, it is very important for a designer to visualize what it will look when it is physically there in your hand. So, and also how well it can be realized, what are the tolerances that a mechanical fabrication has on your design. So those aspects are critical when we design when we take up any of the design activity. So this is a slotted antenna that I was telling about. If you cut slots in a waveguide, then it starts radiating. So this is an array of slots which is there and this is the antenna that is flying in LCA Mark 1 our fighter. And this is the radiation pattern of this, and this is the main beam, and this is the side lobe of better than 28 dB. And then these are also slotted antenna array for air surveillance radar, and these are also acoustic. If you go to an airport, you will see one antenna which is continuously rotating in so many RPMs per minute that I don't know, but it is this type of antennas, slotted array antennas. in some of the airports that are being used. So the other antennas that we work for radars are multi-beam antennas. In this, in this, what happens is the transmit beam is required to cover. It is having a broad beam, but while receive, we have to discern the height of the target. So for that, in the reception, we are having a multiple beams in this multiple beams. So this basically these multiple beams should have low side lobe levels, and the key design challenges that is there for our antenna designer is this antenna, whatever antenna, multi-beam antennas that were designed, we are having an integrated power divider. So in order to achieve side lobe levels better than -35 dB. So this is one of the key challenges when we work for this multi-beam antennas. So these multi-beam antennas have been implemented in many of our radars like 3D car, Rohini, Ashlesha, and Revati. For some Revati is on the ship, and another, all three are on the ground. These are ground-based radars. So one key feature of any antennas of our radars are antenna arrays. Antenna arrays are one of the techniques where you can having a focus beam. For example, if you take a dipole antenna, so it is having a omnidirectional pattern, I told you. So it is basically a donut pattern, only in one direction and a direction in one thing. But for a radar, as I told you, we want to have a focused beam in a particular direction. So in that case, if you combine this number of dipoles in some fashion as an array, so we can have a focused beam. So for example, over here I've shown this is the radiation pattern. Okay, it's only in one scape, so basically it's a circle or something. So isotropic radiation element will have a pattern like this. It will have a radiated field in all the directions. But if you consider it as a 3-element array and combine its output, then you are getting a directive pattern. As you increase the number of elements, we can have a sharper beam. And then this is if they are all in the same. This is only if you control the amplitude. But if you control the phase as well as the amplitude, you can have the scanning possible with this array. So arrays can be, there are linear arrays. For example, this is a typical example of a linear array in a line. A planar array, in a rectangle, you are having a number of arrays. And the conformal arrays they are basically conforming on the antenna surface. So conformal arrays are more in aircrafts and all, they are more prominent because it can be flush mounted on the antenna in the airframe. So these are antenna arrays have impacted, especially not arrays have impacted the antenna's performance in a huge way. So this is how I was telling, like by controlling the phase and the amplitude of the antenna elements. For example, this is the input from the transmitter, you can say, and then the power is being distributed through this feed network, and then to each element we have assigned one phase shifter. So the amplitude will basically, what it does is it basically controls the side lobe level. So here, with the combination of the different amplitude weighting that you provide, and at this point I just wanted to tell, like, there is a analogy to the digital domain on our antenna. For example, if you consider this Fourier transform of a square function, then we are having a sync pattern. So here also, if you consider this antennas and then that sync function, if anybody have just analyzed it, then you can see like the side lobe levels that you consider that you get is around 13.5 dB. So here also, whatever amplitude you are facing here, you can consider if it is an equal weighted, then it is a flat. So it is like a square. So when you transform it, or basically our antenna is a spatial filter. So in digital it may be a time domain filter, but here we consider antenna as a spatial filter. So if you control the amplitude at each element by various distributions, like in filter design we are having Chebyshev, Butterworth, so many distributions so many types of filters are there. So where you will basically control the amplitude. Here also by controlling the amplitude, you can play around with the beam shape. You can play around with the side lobes. So that is how it has improved the functionality of the radar antenna more. So now I would like to go to this case study. So this case study is basically the antenna design for a synthetic aperture radar. Synthetic aperture radar is basically a radar which is installed in an airborne platform. So one unique feature is, if you say radar is, I told you radar is a detection and ranging. So main purpose of radar is only, a conventional radar is basically to only detect and then track the particular target. But if you are using the motion of the aircraft and then you are collecting it, and here also the array theory comes, if you are collecting it and then storing it and finally combining it, you can have a resolution not as good as optical resolution, but in resolution in some submetric range or in meter range that you can construct an image. So this is an antenna that has been designed for one such application. So this KU band, and I would like to, for the audience, I would like to just tell what is the antenna development cycle for any radars. So especially this is for the array type of antenna. So we are be giving the antenna specification, which are being derived from the radar range equation. So those specifications basically are gain, what is the beam width requirement, what is the side lobe requirement, what is the polarization of the antenna, what is the gain requirement, and what is the return loss requirement. All those comes as a specification to antenna. So as an antenna designer, as well as size, weight, those are also critical. So during the feasibility study, we may not take all. For example, cross pole and other noise depth and all also are one of the parameters of this antenna. But we will only take some primary parameters, primary specifications, which basically are gain and the size of the antenna, side lobe level, and beam width. So with that, a feasibility study is done, and to arrive at the different options. So after that, the design, the review, preliminary design review is done, and then the design of the architecture which is being apt for the system is being followed. And then for an array, we start with the single element design, because as I told you, an array is a arrangement of the element in a number of rows in and a number of columns. So we start with the design and development array, and then where we fabricate and test the single element, then we start the design of planar array, and then fabricate, then measurement is done, and then we will go through this flow chart of whether it meets the specs. If it does not, we go for this design optimization again, to go till we reach our road. And then one more important requirement of any component nowadays in any industry or a commercial thing is the qualification, depending upon its usage. For example, if it is a ground-based, if it is to be mounted on a ship, or it is mounted on an airborne platform, the standards of this qualification varies. So, meeting this qualification is also a very challenging aspect of any antenna design, because the material that you choose it, the process that you follow to fabricate it are critical in getting a product which will qualify those requirements of the platform that you are going to use. So when you design it, when that antenna specification, that is also one of the important parameters. So, the components, for example, the connectors that you choose and all should be mil grade if it is for a military application, or it has to be qualified for airborne and all. The vibration levels, the environmental qualifications are very different, because you have to emulate the environment in which the subsystem is going to. It has to withstand those harsh environmental things. So that is one of the important aspects while we consider the design of the antenna. And then once it meets the specs, if it does not meet the specs, then again design optimization or correct material choice, again it goes through this loop. So after that only, not only meeting the electrical specs, but qualifying for that particular platform is also important. So after that only, it is finally ready to integrate with the other systems of the radar and being flown in the flown or being used in the system. So let me give some of the parameters that I just mentioned earlier. We were discussing on it, and then I also would like to give the rationale on which this specification are derived for a particular case. For example, the antenna that I'm going to show is at a KU band. This frequency has been chosen because of the range requirement and weight and size of the component. Since this has to be in an airborne platform, so they want a more gain. So if they go for a gain like X band and all, the weight and size of that component will be more. So that is why, but the weight and size of the component will be more. That is why they have chosen KU band. And then in this weight, this size can meet the pattern and the gain requirements. So these are the rationale behind choosing KU band. But one more thing is that this airborne platform has L-band system also. L-band means 1 to 2 gigahertz frequency range components or antennas are installed in that. But that are a different set of performance, this radiation parameters they have. They may not be having a very high gain requirement, or they may be only for reception, where only a single element will do. So in that case, considering those constraints only, this frequency is chosen. And then the bandwidth requirement for this radar was 1 gigahertz. This is basically defined on the range resolution. As I told you, the synthetic aperture radar is an imaging radar. So if you see the conventional radars, the resolution is basically the ability of the radar to detect two targets separately in space or in range, in azimuth or in range. So, but when you are trying to create an image, you want your resolution to be more. So usually in submetric or meter resolution. So the bandwidth requirement is directly inversely proportional to the range. So lesser the range, higher the bandwidth requirement. And then the polarization, as I told you, the orientation of the electric field is basically constrained because it is used for a ground mapping, so vertical polarized issues. Antenna size, basically to meet the resolution, gain, and fitment in the airborne platform. So these are other parameters like beam width and side load level. We are having difference pattern that is called monopulse. So that was also one of the key requirements. Cross pole, power handling, how much power it should, because that also dictates on the type of antenna that we are going to choose. And then the weight, as I told you, it should be less than 3 kgs. And it should be airborne qualified to meet the requirement. So to start with, as I was telling, like the single element performance in an array is important, and that only gets repeated. And then in order to feed that, in order to control the amplitude and the phase, we will be having the power dividers or the phase shifters. So this is the single element. So we have taken, in order to arrive at what elements can we choose. So basically the criteria was, it should have a white band, as well as when we realize it, it should be easy to realize also. So the antenna topology considered are an aperture coupled patch. Basically, since it is an airborne and a lightweight and a planar configuration was the requirement of the project, so we went ahead with this microstrip configuration. So this aperture coupled patch is basically fabricated in a dielectric, and there is a feed which is going there, and this is a slot in the ground which couples the energy to the patch over here. And this is also a patch which is called proximity coupled patch, and this is a stacked patch area, a stacked patch where we have multiple radiating elements, patch shape only, and there is only a one feed network. So here, the main requirement was a bandwidth of 12%, and these microstrip antennas, even though they are having a low profile and they are very lightweight, easy to fabricate and all, one major drawback is they are a very narrow bandwidth antenna. In the sense, like over here I mentioned a bandwidth of 12%, but a patch which is fed by a single feed, which has only around 1 to 3% bandwidth that you can achieve. So bandwidth enhancement for this can be achieved by this aperture coupled, proximity patch, and stacked patch. So we considered these three configurations. In this, we found all were having merits of bandwidth were achievable by all these all the antennas. But the realization aspect was important over here, because at KU band your frequency is around 16.5, and then your dimensions are very small. So this alignment of this single element realization is okay, but when we are considering it in an array, the alignment of this coupling of this this slot and this feeding was critical. So that is why we did not consider this as a radiating element. And then the same was for this proximity coupled patch. We chose stacked patch, even though it had multi-layer structure. Only thing was because in the patch over here can be directly fed, and then this patch over here is electromagnetically coupled. So this had no issues of alignment, and that coupling also it was resolved in this. But the only demerit is this is having a multi-layer structure, so we need to take care during the fabrication of the antenna. So this is the performance of the patch at the EM software that we have used. So we have done in HFSS, and this is the stacked patch configuration. This is the ground. This is one patch over here, and then in between this patch you need to have a spacer. So here there is we have not gone much into microstrip antennas, but this is one technique of increasing the bandwidth by increasing the height of the patch and by using multiple resonators. But the multiple resonators in this multiple patches. So this has an advantage of we almost got around 2 gigahertz bandwidth, and this is the radiation pattern over here. And then you can see here as compared to this plane pattern. This is one plane pattern. I was talking about E plane and H plane. This is one plane and another plane. Here you can see as compared to this pattern, there is a small field coming that is basically contributed by this feed line which is there over here. So these are some critical aspects that one has to see while designing the antenna. So this is the performance of this patch antenna. This is the return loss, and this is the radiation pattern, and this is the cross pole pattern for the antenna. So now going to the design of the planar array. So we will start with the array specification, then arrive at the array architecture, and then depending upon the beam width and the side lobe. So here we were more concentrated on the beam width and the side lobe level. So once the gain is fixed, we know like what is the aperture of the antenna. So now when we are considering the planar array, we will be considering the beam width and the side lobe level. So we will do some pattern performance analysis in Matlab, then get the feedback, and then again do it. Then we will do this power divider, which is called RFManifold in our terms. So we will do the design of this, and then it is simulated in EM tools. The optimization is full done, and then whatever values we get in this electromagnetic tool, we will try to map with the Matlab simulated pattern, and then integrate the power divider with the radiating element simulation in the EM tools with the antenna element, and then we go ahead with the prototype development. Then we go for validation by testing, and then if any further optimization is required, we will do that thing, and then again we qualify it. So this is one flow that we follow during the design of this passive antenna array for any radar. So to meet those electrical specifications that I mentioned for the KU band antenna array, so we came up with this architecture. First is that stacked patch. So this is an array. So the one which I showed was a single element, and then the consist of stacked patch, and then it consists of a hybrid feed. Basically, one is this microstrip level feed, and then the other is this waveguide feed network. That is why I am calling it as a hybrid feed. And then there are 512 elements arranged in 16 by 32 rows, and then the feed consists of a microstrip feed network is at this end, and there is a waveguide feed network in this end. So a portion of this microstrip feed network is fed by the waveguide feed network. So the one important aspect is one transition that has to be done from the waveguide to the waveguide feed network to the microstrip layer, and it has to have a azimuth pattern in the for this antenna array. Monopoles pattern, azimuth monopoles in this array. So as I was telling, we go ahead with the Matlab simulation first. So to achieve this 25 dB distribution, I went ahead with a Taylor 30 dB distribution. So these are the pattern. This is along the 32 azimuth. In the azimuth there are 32 elements in the X. So this is the azimuth pattern. In the Y there are 16 elements. So this is the elevation pattern. This is the simulated, and this is a very ideal pattern without any errors and all. So then we come to the RF manifold of the power divider architecture. As I was mentioning, it consists of two levels of power divider. One is the microstrip feed and another is the waveguide feed. So this red color is the waveguide feed, and then here is the transition which is there, which will couple the energy from waveguide to the microstrip feed. So this is how the layout looks like in any CAD tool. So as I was telling, there is a patch. There are two patches, okay, and then there is a separator that we have used Rohassel, and then there is a waveguide feed network. And then for the design of this power divider, we are having the design criteria of amplitude imbalance of plus minus 1 degree and plus minus 5 degree as the phase imbalance. So this is the design of a waveguide power divider. So we have chosen a hybrid feed network basically because the requirement of power handling of almost 300 watts for this system. So that is why we went ahead with this waveguide feed network as the first level, because from the transmitter the power will come and then will couple to this waveguide first. The microstrip will not be able to handle that much of power. So that is why we are going ahead with this waveguide feed network, as well as the main reason is if we try to implement all these power dividers which are shown in red in the microstrip only, then the radiation, because I told you in the definition, like any metallic object will radiate. So along with the patches over here, the line also will radiate. So overall the efficiency of the antenna will come down if we go ahead with the same layer architecture for this same layer of power divider realization in this antenna. So that is why we have gone for two-layer level of architecture. So over here, this is basically consists of an H-plane waveguide configuration, and then here the length and the basically the power is controlled by optimizing the length and thickness of the septum, and this full analysis is done in the HFSS software. So as I was telling, this is one of the waveguide power divider, and these are the power levels that are to be simulated in the it have to be simulated and optimized to get the particular size of levels and the beam. So basically here is the septum, and here is here are the irises, two irises over here, which will basically optimize the return loss as well as the power levels that we get in this port 2 and port 3 of this waveguide. So individually we will optimize and then integrate it and then analyze the full structure. Now the software can analyze, we can also carry out sensitivity analysis over here, in the sense like when fabrication, if there is a certain tolerances of some microns, so what is going to be the effect on your final antenna performance, that can also be analyzed in this software. So that gives us a fair idea on what values that you can tell to your fabrication guy, telling like, okay, I am having this performance will degrade if you exceed this tolerances value. So with this software also you can do that, and basically this is one of the performance of an antenna. So here we can see like the return loss is better than 20 dB. The phase across, this is some around 2.2 degrees, so phase is around minus 1.5 to 1.5 degrees, plus 1.5 degrees, the phase variation across the frequency in this design. So the other net feed network is this microstrip feed network, where we have used this 4x4 element. The patch element is fed by this microstrip feed network. So basically we have gone ahead with this corporate feed network. Basically it gives us wide bandwidth, and it is basically T junction. So basically this T junction is composed of this impedances. By controlling the impedances of the line, we will be able to optimize the powers which is coming at the two ports of this network, feed network. So this is a typical layout and the circuit in an ADS software. And these are the performance of this 4x4 and 2 quadrants power divider performance. Actually, dispatch, this does not include dispatch. Actually, I have just indicated these blocks to highlight the power values. Please don't consider this as a patch. These are all the power values indicating that is to be there. So here actually, here also the return loss is better than 10 dB. These are various power levels, and then all the ports we are seeing the frequency. What is the phase response for all the outputs of this power divider? So one very critical portion of this design, and most of my effort went in the design of this waveguide to microstrip transition, because it had to have a low loss and it should match with the, because here what happens is this waveguide we are having a T mode of propagation, while microstrip is a quasi-TEM. So not only impedance matching, mode matching is also required. So here we have done with a this is the transition pin. This is like equivalent to a coaxial pin, but slightly different in the sense like this is going to sit on this microstrip layer. So here, this being a KU band, the dimension you can see here, it is only 5.3 mm, and the dia is 0.8 mm. It is smaller than this smallest stapler pin. So this realization is also a critical aspect at KU band frequency. And then it was simulated, and then we fabricated and tested a back-to-back transition. So this transition loss was less than 0.5 dB for the frequency of operation for our design. So this is the full waveguide power divider integrated with the microstrip transition, and this is the performance of the waveguide power divider. This rate is the return loss, and others are the power values. So here I would like to present the comparison between the ideal and the simulated amplitude and phase. What you can do is we can get this power values simulated in the software and then map it onto the ideal value that we have seen. So the design constraint that I had put for that power divider of plus minus 0.5 dB for amplitude and plus minus around 0.5 degrees for phase. Actually, so even we have optimized this in the EM simulator, but since as we saw, like there is a variation of plus minus 1.5 degree in phase also, so those all will attribute in the silo level. So we can see here this silo level has come up, the second silo level also has come up. So these are all the amplitude and phase errors that has been there in the while designing of this waveguide power divider. But since our specs is less than minus 25 dB, so this performance is okay for us. So that is why when we are designing any antenna, so some antenna system, this give us a spec of some 25 dB silo level, but as an antenna designer, when we start designing, we take a Taylor distribution of 30 dB or 27 or 35 dB, so that when these errors creep into the final, because they will be there, because your design cannot be 100% ideal. There will be some variation across phase, variation across amplitude. So that will eventually culminate into this. So in order to achieve the system specs, we always go ahead with a little higher Taylor distribution to be implemented in this field network design. So the full antenna was simulated in a 3D software. So that is what I was telling, like now the computational speed, computational capability has increased. So maybe 10 years back, we would not have been able to simulate this full array of almost more than a half a meter and around a quarter in around length. So, but thanks to the computational capability now, that we could simulate this full array integrated with the radiating element, with the feed network, with the transition. So this is the simulated VSWR or return loss. It can VSWR and return loss are also our specs was less than 2. So we have in the simulation we could see like it is achievable. And this is the radiation pattern in azimuth plane. This is the elevation pattern. So this is basically, you can see here, there's a smooth bow coming here. Like we can see like a sync function, how it is. But since this, along the azimuth, along x-axis, there are around 32 elements. So we are able to properly control the amplitudes properly, and then we'll get this type of pattern. But in the elevation, the number of elements is only around 16. So the control of amplitude and all will not be, will restrict in getting that pattern. Nonetheless, we are getting the specification for the antenna. So this is the monopulse in the azimuth plane, and this is the main beam, and this is the ideal pattern. And then I have put it simulated and phase values that we did in EM simulation, and then finally the EM simulated pattern that we have finally got in the result in the 3D EM software. So this I have mapped it. So you can see like from the ideal value and then the EM simulated how it gets varied over the design. So this is how we have, this is the elevation and this is the azimuth pattern. And this is the fabricated unit on the top, and the main criticality was in this multi-layer architecture. So here the workmanship is essential, as well as it required bonding, as well as bonding with this metallic frame. So this has all been taken up during the fabrication people, and our mechanical as well as fabrication team did a good job in getting the process right, so that we could qualify it. And this is the comparison of the simulated, and this is the measured. So we can see like it's almost following the curve that we could get in the simulation. And this is the measured pattern in one of our measurement facility. And this is for the azimuth pattern, and this is the elevation pattern. And I would also like to share some of the antenna elements that are widely used in some of our radars. This is a typically printed dipole, and this is a cavity-backed patched array for most of our ground-based radars. And this is a meander line antenna. This is also a printed antenna. This is a dipole at X-band. This is an L-band metallic dipole for IFF. This is a dipole antenna, but due to the space restrictions, the designer had to tweak the antenna construction such that it gets fit in the space. So that's what, like, we all have to think uniquely sometimes to accommodate requirements, especially the space available. And this is one of the antennas which is conformal. This is at X-band. So if you see, like for an antenna engineer, finally the performance has to satisfy the radar requirements. So, for example, that ECCM features, like it should be tactfully, the radar has to be tactful, in the sense it should be able to not get deceived by any other like jammer and all. So those requires, like, you have to have a frequency agile antenna, like it should operate in multiple frequencies, or it should be having a number of frequency spots so that your antenna is frequency agile. It should have adaptive beamforming depending upon the scenario. The radar may require, like, sometimes it may require a wide beam. But for example, if it is only surveilling, it is only doing a surveillance application, at that time the radar may require a wide beam. So, but when it is tracking, when it is particularly dedicated, it wants to dedicate its energy to a particular target only, at that time it wants a narrow beam. So at that time it requires an adaptive beamforming capability. So in that case you should have a wide bandwidth, and also it should be agile. The antenna should have that feature. It should be able to scan a wide volume of antenna. So in that you should have a wide beamwidth. And then when we consider of array, there is something called a array scan blindness. What happens is basically this is encountered in basically in electronically scanning radar application, where your antenna is.
Ma'am, sorry for the interruption. We have last 5 minutes
I'm
left.
Almost done. Yes. Yeah.
Yeah.
So,
Okay. Yeah.
This called array scan blindness. So where at a particular angle, because of the mutual coupling that is existing in the antenna, the EM radiation does not happen. The energy, electromagnetic energy is trapped in the antenna itself, and it does not radiate. So that is called scan blindness. So that you have to consider. Your antenna should have low mutual coupling and low cross pole, and then low cost array. As I told you, cost is one important factor. So your antenna design should have it should be low in cost, and lightweight arrays for airborne antennas. So you have to choose a correct antenna element to meet this requirement. So these are some of the phased array radars that are electronically scanning radars of LRD. And the future of antennas for radar is now a lot of functions are being incorporated in the radar. For example, we don't want our radar to simply act as a radar, but it should have an IFA. It should have electronic warfare components in it. It should also be used for communication. So, but the research is still going on, and that the solution is this shared aperture radar. So where a single antenna, so here also antenna has a huge responsibility over here, so that it can combine the functionality of single antennas into a single aperture, so that all these functions can be incorporated in a single system. So the other is the cognitive radars, where antennas can play a very crucial role in the sense like we can have reconfigurable antennas, like frequency reconfigurable. Now in communication, it is already there in order to utilize the bandwidth, in order to increase the, so you already have that frequency reconfigurability. Polarization reconfigurability is one aspect which is used in mapping, used in most of the radars, and also this pattern reconfigurable. So these are all important areas where research is going on for radars. So thank you so much. I would like to end my talk over there.
Thank you, ma'am. That was really a wonderful talk. I would request our participants to post any questions if you have in the chat window. Any questions from the participants?
Manjushree, any questions directly reported to you?
Somebody has. No, ma'am.
Okay.
No, there's one interesting question from Dr. Raghavan. Sir is from NIT Trichy. He's been there with us for almost all the events. Thank you so much for joining, sir. And he's a wonderful person who's been working in this microwave field for almost 40 years in NIT Trichy. Thank you so much, sir. And his question is, in this digital world, in many engineering institutions and universities, the most important course, radar, is totally removed from the syllabus. He's asking, is that good, or at least from the EC branch of point of view, should be this radar subject should be included in the syllabus? That's his question.
I would like to answer this. Thank you, sir, for this question. Sir, what I feel now is that instead of very specific like radar, I would suggest, especially the fraternity of academia and all, that more emphasis can be laid down on these principles of electromagnetics, so that the students get excited with that subject, because radar is just one manifestation of electromagnetics. There are other areas like communication, and now this communication like 5G and all those things. Now, as I was telling, radars in autonomous vehicles and all, but I would really, it will be a very helpful for the students, as well as if an interest can be brought out in the students towards this field of electromagnetics, because I know like nowadays whomsoever we want, in what field they want to work, they will tell, I want to work in digital, I want to work in FPGA, or hardly few engineers would like to work in this field of electromagnet. So it would be good, like if the foundation because I personally, I also felt like when I joined my establishment over here, and over the course only, I also got fascinated by this field of electromagnetics, because I was thinking, yeah, all the things I had learned in my physics in my 12th, because electromagnetics is electric and magnetic field is a topic that has been taught, I think, from 11th, 12th, but on the due course of time, I don't know, maybe because of the digital lure or something like that, the interest slowly dies down. But I feel that there's a lot of potential in this area. So that would be more instead of specific radar topic. It is more.
Thank you, ma'am. And there's one more question. Is LIDAR and radar, which is the best? Could you please suggest?
Pardon? Radar and LIDAR.
Yeah.
Radar. Okay, LIDAR is basically a laser, right? So radar is basically using electromagnetic waves. So LIDAR, I only have read some thing on LIDAR. But one thing is, I think like LIDAR is a little bit harmful, like operation and all will be a little bit harmful. And radar and LIDAR is basically, I think they are having a very high resolution. But this radar and all, as compared to LIDAR and all, the resolution is slightly less. But the cost-wise and functionality, I have not much experience on this LIDAR. So only those two aspects I can tell you now, ma'am.
Actually, I just want to add on to that. See, LIDAR, now we have a directed weapon and lasers coming into picture and as a combat and lethal weapons. So this LIDAR, of course, has a application in that, which is a directed energy. We can point out at the directed energy can be pointed to the designated enemy, but it is an enhancement to the radar. Radar is a all-weather, all-weather sensor. So it can reflect. So thing is that all these things together in any platform makes enhance its capability. But as such, radar is a primary sensor. So applications are multi-applications, as Dr. Raghavan has also asked. Right now, if you see whether it's a drone thing and whether it is aircraft, helicopters, ground-based, lot of things you mentioned, and everywhere this radar is there. So thing is that, but an autonomous vehicle, but thing is that as he was asking, the radar subject itself is removed from the topic because, I mean, the communication, the field is more commercial and all, and this radar aspect, if we see, except the autonomous vehicles, mostly it is in military and defense application or spaceborne application. That's why it is not much talked about. So, and one more question, Manjushree, I want to ask. Actually, from antenna design perspective, you have covered from military aspects. And can you put some more on, like we are all talking about mobile and the antenna design for this 5G, which is more a very hot topic nowadays, the current technology. So in that, any advancement, can you just, if you have any information on that?
No, this 5G.
Yeah.
Hello? Yeah. This 5G and all are more going for this integrated approach. For example, now 5G has two spectra. One is till 6 gigahertz and another is at Ka band, that frequency. So on that aspect, this most of this they are basically electronically scanned antenna arrays only in the 5G also. But from the realization point and design point of view, they are going for this integrated approach because now they want the antennas to be very compact. So now they are going for this multi-layer architecture. wherein the if you say in phased array, these TR modules and all are integral part of phased arrays, no ma'am. So this TR module and all are also, they are stacked up together. They come in a very small form. So
Okay.
so more in the designing of a compact antennas for 5G. So
Okay.
yeah.
Jessica, any more questions?
No questions. There's an information shared from Raghavan sir. His scholar, Dr. V. Krishnakant, got rupees 5 lakhs from DRDO as an award for his work on FSS. That's really nice to know, sir. So
Okay.
I think there are no more questions.
Okay.
Yeah.
We can conclude then. Sadhana
Yes,
ma'am,
ma'am.
can we conclude?
Yeah. Thank you so much, Ms. Manjushree, for giving a very elaborate talk on radar design. It was very enlightening, and I'm sure it was useful. And this is the last talk of the WDRD webinar series. I would like to thank Reena also for having arranged this talk, and I would like to thank Ms. Jesudha for having hosted the event, and I would like to thank all the participants, especially thanks to Professor Raghavan, who's an active member in all the WE webinars, all WE programs. He's always there. He was there in our first program also at Infosys for International Women's Day, and this is almost the last program of WE. Thank you very much, Professor Raghavan, for always encouraging us and being with our activities. And I would like to thank all the participants who are here through the webinar. Thank you one and all. And I think before we leave, we can take a group photo, Jesudha. We can switch on the camera and put that DRDO webinar series poster.
My
Yes,
camera
ma'am.
is not working.
Yeah, and then we can take one group photo for our AGM also. We can use it.
My camera is also not working.
No, I suddenly stopped. Oh, now it is.
Jesudha, you can click it. The speaker's camera is not on.
Yeah, ma'am. Actually, from that time, some problem came up.
And if we can put that webinar poster, it will be good.
Put it in F5 mode actually. Full screen mode.
Yeah, okay. Thank you, one and all. Yeah, speaker, if it can switch on your camera, it will be good.
I will try to, madam. It is coming intermittently. It is going. Okay, it came for some time, madam. It will go.
Yeah. Okay.
Yes, ma'am. It's done.
Yeah. Okay. Thank you.
It's again gone.
You can conclude, Jesudha.
So thank you all for joining.
Okay, thank you so much, ma'am.
Reena, you would like to add anything?
No, ma'am. Thank you actually for giving this opportunity for DRDO webinars, especially for women speakers, because otherwise, this is first time I think I tried from DRDO, this women speaker series. So, and you have allowed me, it has given a little bit of, this is first time we have tried, then we can continue further, as a woman.
Yeah. I think we can continue next year also. Maybe we can continue this.
We'll have the optimization of time and schedule and slot and like that, because next time hopefully this corona thing won't be there, so we may have some physical this thing also, not only online session.
Yeah.
Thank you, ma'am.
Okay, then thank you all.
Thank you.
And please join us for our AGM. WE AGM is on January 3rd from 11 a.m. to 1 p.m.
Okay.